So the first question many people ask me is, Intel, Scala. Intel, Scala. They don't get it, and no one gets that. It's actually because Intel they see Intel as a hardware company, but Intel is not a hardware company anymore. Intel does not do only CPUs anymore. We got beyond that like 10 or 15 years ago, although we have not advertised that so much. So can you guys hear me all right? Cool. So Intel does things like SSDs, network accelerators, and for the longest time we have been trying to optimize languages and other systems to run faster on top of our hardware, like Java. We have been 10 years optimizing Java, Python, Node.js, and now last year we started working on Scala. And I have to say that all the work that we're going to see today is going to be open source through GitHub. So don't think this is an effort to sell you anything. We don't want to sell anything here. We actually want to show to the community what we have done, and we want to give back. And we would like your input as well. So everything that you are going to see here is going to be open source through GitHub. And the presentation obviously will be online. So what is the agenda for today? What are we going to see today? So today we're going to see, we're going to show a Scala benchmark that we have been working on based on big data workloads like Adam, like Spark. And we are also going to show a case where we have optimized Scala, one of the libraries of Scala actually, to work faster with one of our benchmarks, and also to work faster with one of those big data workloads. And actually, I'm going to show how any one of you can do it once we put this online in a couple of weeks. You can go to GitHub and extend it. You can create new benchmarks, micro benchmarks. It will join the main thread. And it will be, I think this can be we think that this will be a very good starting point to create a benchmark suite in Scala that is big data related. And we think that this talk will be interested for not only people who optimize Scala or are language developers of Scala, but also for Scala apps developers, big data app developers who use Scala. So you guys know if, for example, the feature you want to use is actually a bottleneck in Scala or it's actually in your program. So that information can be useful when you are trying to optimize your servers or your service or microservice on your cluster. So I am a performance engineer, data center performance engineer, and I've been at Intel for 5 years. Many people ask me why I'm not a manager yet. I like my job. So anyhow, in the last year, we started looking at Scala performance. And the Scala performance, one of the few things that we look at it was like, where are the benchmarks? Like we have a Scala bench, for example, but the Scala bench is somehow outdated, and the workloads are not related to big data at all. So optimizing for a Scala bench will not help truly optimizing for big data workloads like Spark, like Adam, like genomics. And SparkBench, for example, running a SparkBench doesn't really. SparkBench is focused on Spark. It's a benchmark for Spark. It will help optimizing for that. It will help Spark directly, but it will not help Scala. So, and then we found a bunch of micro benchmarks online, but so with a lot of limitations. They were not actually descriptive of any big data workloads. So the main problem when you want to run your own benchmark or micro benchmark in Scala or big data benchmark is you need two things. The first thing you need a full configuration of an Apache Spark installation. And the second, and most important, is your own cluster. So this is really, really expensive. So we thought, what about if we extract those, using those big data workloads, we extract those bottlenecks, those pain points, and we create a lightweight Scala benchmark suite. And that way, it's much easier to use this benchmark suite to get profiling data from that bottleneck over and over and optimizing the bottleneck than to run the entire stack and to run the entire workload. That will take hours. So this way, you will not need an entire cluster to accelerate, to get performance information or profiling information from a big data bottleneck. So you will not need a cluster anymore or an entire Spark installation. We have extracted all that information and condensed that on a benchmark suite. And the benchmark suite, the code itself looks a little bit strange, but that's because we have tried to get the data patterns, the algorithms exactly, and the usage of Scala libraries as they are from big data. So this is the minimal expression that you need to actually express the same bottlenecks. And you can run this in your own machine. And moreover, it has things like, so this will allow you to optimize, to run this benchmark in minutes instead of hours, like before. So this is the main difference. And this is actually a great advantage compared with before. It also has features like it will give you throughput information, garbage collection information, memory allocation, thread synchronizations, the just-in-time compiler, Java just-in-time compiler, JVM statistics, all in one benchmark suite that is actually easily expandable. So this is actually how we created all our benchmarks as part of the suite. So the first thing that we did was to run big data workloads in a Spark cluster that it has been between 80 and 90% optimized. And the way we did this is that my team at Intel, we focus on optimizing data centers. And we grabbed all that experience, 10 years of experience optimizing data centers, and we created a very optimized data center, 80 or 90% fully optimized. Why 80 or 90, not 100? Mainly because depending on the workload, your optimum point moves, right? So we grab a midpoint where all our big data workloads are pretty much optimized, 90% or 80%. And this is the first part, right? When we are trying to do any performance work, we need to eliminate all the bottlenecks because of Spark itself, because of the JVM, the JIT compiler, the garbage collection, the Linux kernel, SSDs, network connection, server configuration, all that stuff fully optimized. So bottlenecks are not because of that. Bottlenecks are purely because of Scala or Scala libraries or the Scala compiler. So all those places where those bottlenecks could be are off the table right away. And we run our big data workload. In this case, Big Bench, for example, TCPx-BB Bench. And we extract a bunch of profiling data from running that in our workload, in our cluster for several hours. We started profiling information, and from that using that profiling information, we actually create a benchmark. And that benchmark will run for minutes. So we had our cluster running for days, sometimes days. We extract that profiling information, we create this benchmark that we only need to run for minutes to obtain the same bottlenecks. And we include that in our suite. And we actually repeated this process over and over to extract more benchmarks. We usually have one benchmark for each bottleneck that we found. And we repeat this process as well for each workload. For example, GATK is the genomic analysis toolkit developed by MIT. SparkBench as well, we run it. We obtain a bunch of information from there. And Adam Genomics as well. So we found bottlenecks from Adam Genomics. And these are some of the bottlenecks we found. Like, for example, the mutable hash map, the mutable tree set, the array buffer, we found them to be some kind of bottleneck in certain situations, especially for the data patterns that we are seeing in big data. That's also the main problem. When we write a micro benchmark, performance engineer write a micro benchmark, or anyone writes your own micro benchmark, is the input data you're using related to the big data or not? It's really one input related to genomic big data analysis or not? And this is exactly how we found these bottlenecks. Because with the right input, you can point this out. And we're going to show an example. later in the next slide. In this slide, this is how it works. For each one of these benchmarks, we grab our driver that we develop, grabs each one and runs it. And by running it, it actually it runs in minutes instead of hours, and it also allows time-based profiling. And let me explain time-based profiling a little bit more. So when we run any benchmarks, usually we say, oh, I want to run this, I don't know, do this array update operation for like 10,000 times, right? Let me tell you something. In Scala, you are running on top of a JVM, the Java Virtual Machine, and a just-in-time compiler. And it takes time for those things to warm up. The same with the cache, the OS caches, and your CPU caches. All that system takes time to warm up. It's not enough with running 10,000 times array update, for the function array update, for example, for 10,000 times, because that can be 0.1 microseconds in your cluster. And your cluster cannot be warm enough, meaning you will see more compilations in the future done by your just-in-time compiler. You will see more garbage collection getting done than usual. But there will be a point in time where all those things will stabilize, and it will be a stable point. And that's where we get all our measurements. That's why this benchmark suite has a warm-up sequence embedded in it, so you don't need to worry about that anymore. You are going to see how this workload will perform in your cluster long run. Because that's the main thing, right? When you do your run in your laptop and you put it on your cluster, it's not going to work the same. Why? Because usually when you see in your PC or your laptop or desktop is non-stable performance. And what you see in your cluster is long-running workloads, long-running performance. And this is exactly what this benchmark suite will provide to you, that type of data. And also, it does dynamic input scaling, so it will dynamically change the size of the input. So you know how is the scalability of the algorithm you have been developing, or the scalability of a certain Scala feature. And well, we also get more information like thread synchronization, call stack, as I said before, memory allocation statistics, throughput, and the Java file recorder. You don't even need to worry about how it works. You just get the data, double click, and boom, a bunch of information appears. It also allows us to compare different Java and Scala versions. And that means that sometimes it's very hard to know which Java version shall I use, which Scala version shall I use, because believe me, using the latest and greatest Scala version or Java version can be counterproductive in terms of performance sometimes, depending on what you are doing, depending what feature you are using. And this is one of the example output. It also gives, besides, it's basically, right now, it's a very poor Excel spreadsheet with a bunch of data. We're still working on that. This is like the beta release. And also a flight recorder, a file which contains most of the data. And it allows, as I said before, it allows to get the throughput for different sizes, scaling the sizes for you. No need to touch anything. It also will perform different permutations of different Java versions and different Scala versions. So you know exactly how this feature will perform with different JVMs and different JVM configurations, like, for example, heap size and different Scala versions. And the best thing is that the only thing you need to do is to click a button and wait 30 minutes. And this is one example where we have successfully used this technique to actually improve something in Scala, finally. So the thing that we have improved and we have not yet released the code is the mutable hash map. We found that with a certain pattern, the mutable hash map in Scala is very interesting because it performs very well, but under a certain input pattern, when we are inputting data into the hash map, under a certain input pattern, this hash map actually becomes overloaded. And its performance changes from big O1 to big ON, basically a linked list performance. We found out that we need to update the best way to go with this performance issue was to update the mutable hash map in using a opportunistic red-black tree. And basically what we do is that we use red-black trees inside the hash map opportunistically whenever we see a good situation to use them. And that changed the performance of the worst case scenario from ON to O log n. And believe me, folks, this increases the performance of Adam genomics, even though it doesn't look related, but all the way, these changes go all the way to the stack, where the point where Adam genomics work faster, thanks to this change. This is an example benchmark that I wrote just as an example to see how you can create your own benchmark easily. And the only requirement is basically needing to extend this trait that we created. We created a trait with two empty methods that need to be defined. Those two methods, the warm-up and the run. And basically, the warm-up is just to, it's a warm-up sequence that the driver will run, and it's the run sequence that the driver will run with different sizes. And why we did it this way is actually to hide complexity. So the driver is actually very complex, and your benchmark can be as complex as you need, but the interface is as simple as possible. It's just two methods. And that's the only thing that with actually one argument each. So the driver only understands those two methods, and all the complexity is hidden from both sides. So that's the beauty of it. You can create your benchmark as complex as you want inside, but you hide all that complexity away from the driver. So this is just the conclusions. We built a Scala benchmark suite based on big data workloads, and that allows us actually to simplify the optimizing Scala. Because if I would have to run this benchmark over and over in my main data frame, in my data center that we had at Intel, it will take hours, days. So every time I do a small change, it takes me days. That's crazy if I want to get quick iterative development, right? So by using this performance benchmark, we can do the same thing in minutes. And we want, our idea is to keep updating this benchmark suite right now with more and more benchmarks as we see more and more bottlenecks in the future. And we actually would like to encourage the community, you guys, to actually contribute, be part of the effort, because I think this is a game-changing effort nowadays. It's a way that, for the first time, we have benchmarks, big data benchmarks for Scala. And for the first time, this is going to be stable and maintained, hopefully, and it will be part of the community. So this is some links from the benchmarks that the big data workloads we have used. And this is my contact information. And without anything else, thank you, folks.
When you say big data, what technology stacks are included? Is it just Spark or other? Do you have metrics around Akka and other systems, or is it streaming, not streaming?
That's right. So the workloads we are so no, we don't. So Spark itself. So right now, all our workloads run on Spark, but we have an entire stack, right? We have a JVM, we have a Linux kernel, we have a JVM, we have a cluster manager, we have a Spark manager, we have Scala obviously in the middle, and I think Akka is up to a certain extent is part of a Spark as well. So that's the stack we use. I don't know if that answered your question or not. Okay. So it's actually more than spending a long time, right? So maybe the question could be rephrased as, how do you guys determine what is actually need to be go in a benchmark, right? And once you have that benchmark, what do you do, right, with a benchmark? Is that right? So the way we determine if it's a benchmark is not about how long it takes, for how percentage of time we spend on that point. That's actually one of the measurements, but there are other measurements, right? Like, for example, call stacks. Even if you don't, even if a function doesn't spend, even if you don't spend a lot of time in a function, that doesn't mean that function is not blocking you, because you might be waiting for the function to come back to you in a asynchronous system. I don't know if it makes sense. Like, you're waiting for a resource to get freed in a data center. It's not a function, it's an actual resource. It's like, for example, a SSD, a hard drive. That's not going to show up in your hot methods, let's say, in your profiling information per se, right? But you're actually blocking your system because of that. System information, Linux kernel calls, right, that they need to get optimized. We also see those things. Also, CPU cache misses. It looks like very, very low level, but if our CPU cache misses, I know this for some people may sound like black magic, but we also look at CPU cache misses, and 5% more cache misses in a CPU means 20% of your performance is gone. That's because your access, the way you access your data is the way you access your data. Your cluster manager cannot keep up with you accessing your data all over your cluster. So that type of information first tells us where the, let's say, hotspot is. Hotspot, I don't mean the JVM, I mean a spot where we take a lot of resources. Time is one resource, but there are other resources, right? So that answered your question? Yeah. And from there, we extract benchmarks. Do we use tungsten? I think the workloads we are using right now, they partially use tungsten, but I'm not really sure to what extent. I know, let me think. Tungsten itself, right, is part of a Spark itself. It's not that there's a switch like turn on tungsten. Well, that is totally true. In theory, tungsten should help with cache misses. For example, this is actually cache misses was an example, right? It was not like the centric point. It was just an example. But talking about tungsten, I know it also depends on the workload. I am not sure. I will need to come back to you. Maybe you can email me, and I can come back to you if our version of Spark has tungsten, and if the workloads that we run on top of Spark, they have tungsten, they use tungsten or not. I believe some of them do, some of them do not. But I am not sure which one. So I will need to actually check that and come back to you.
Another question about that, are you benchmarking RDB or data?
Sorry, say again?
Are you benchmarking RDB or data?
So we are working, the benchmark we are using, some of them use data frames, some of them use RDDs. So it's not that we are benchmarking Spark itself. It's that we are using workloads on top of Spark. That some of them use RDDs, some of them use data frames. So it's not that we created those workloads. It's that those workloads are already out there. People are using them and we just grab them and run them. So it's not that we are profiling RDDs only or data frames only or tungsten only in terms of inside the Spark. No. It's that we are at a higher level running workloads that are big data. And those workloads, sometimes they choose to use data frames, sometimes they don't use, they just use simply Spark. Does it make sense? And they use each workload may require a different version of Spark, so Tungsten might not be available. So that's why I'm in doubt up to what extent Tungsten is enabled in those workloads. So right now, the question was if is there any user interface to capture all this performance data and show it to the user? So to be honest, right now the user interface is quite poor. We have worked more on the engine type of side, and it's actually just generating an Excel sheet and a Java flight recorder file. And the Java flight recorder provides a lot of information, and you can actually just double click on that. If you have Java installed in your PC or desktop or Mac or whatever, it will actually open up the very nice interface of Java flight recorder. And that will give you like 50% of the information. And the other 50% is on a spreadsheet that is easily available and readable. So we are working on that, but we have not put all our efforts on that. That's true. Okay, another question there? Sure. Tungsten.
But it's this question. If you've got these different workloads
Mm-hmm.
that you're using to generate the benchmarks, you run into issues where, because different workloads are going to exercise different parts of the system, it's hard to figure out where the actual bottlenecks really are, because you've got different things you can get different ways, or do you have a way of, like, saying, if you're doing this kind of workflow, you're going to get these kind of bottlenecks versus this kind of workflow giving you these kind of bottlenecks. Does that make sense?
I'm not really sure I follow the question.
I guess what I'm saying is it possible that if you cover the system with such a variety of workflows, that you'll actually sort of average out everything
Mm-hmm.
and not really see where the hot spots are, because some things work really well and other things don't, and then they kind of average each other out.
So yeah, so I think now it makes sense. Thank you. So I guess the question was, since we are running such a variety of workloads, how can we determine what is a hot spot, because all the workloads will average out? Well, the way we obtain or profiling information is actually on individual basis and on individual cases. So believe it or not, the hot spots that they do not average out, and we take each individual case as let's say, as a pain point or a benchmark, a way to create a benchmark. So for example, we said that Adam Genomics, under certain conditions, uses the mutable hash map, and we optimize that. Does it mean that is that actually something that we are not going to see at all in other benchmarks? That's true. That's totally true. But that's only one benchmark inside a huge suite, right? It's just one pain point that we want to highlight by doing that. It's not in all the benchmarks that we have in the suite. It's only one benchmark inside a suite, right? So each benchmark is in charge, let's say in charge, or was created with highlighting one pain point in mind, right? So does it make sense? Does that answer your question?
Yeah.
Mm-hmm. Yeah. Next. I guess that's all. Well, thank you so much, and thank you, everyone.